All right. Welcome, everybody, to the SEG Europe Regional Advisory Committee technical webinar series, Geophysics for Today and Tomorrow. In these webinars, we try to bring technical presentations on a wide variety of topics pertinent to exploration geophysics. And so today is our first webinar of 2026 as part of that series. And before we begin, and I turn it over to Brad, we have a few housekeeping items. If you have a question for Brad, our presenter, please enter your questions in the Q&A box that should be on the right-hand side of your screen. And if he has his slides numbered, so if you want to put the slide number with your question, that'd be great if it's regarding a specific topic on that page. Otherwise, just put your questions in the Q&A chat box. So today's presentation is by Dr. Brad Carr. It's on geophysical characterizations of sedimentary uranium deposits in the Shirley Basin, Wyoming, USA. Dr. Carr obtained his PhD in geophysics at the University of Wyoming in crustal reflection seismology, is a senior research scientist in the Department of Geology and Geophysics, and the director of the University of Wyoming's Near Surface Geophysics Instrument Center, and a lot of other awesome things. So before I turn it over, I just want to thank you for attending, and take it away, Brad.
Okay, thanks, Lori. Good morning, good afternoon, wherever you happen to be. Today, as Lori mentioned, we're going to be talking about geophysical characterization of sedimentary uranium deposits, and we're picking Shirley Basin, for just a type region that hopefully this study eventually will give us more sort of general characteristics of uranium deposits and sedimentary basins, but as you all may know, there's different environments for uranium deposits. Than this is just one avenue that of those deposits. This is a little different, usually lower grade than say things like the Athabasca Basin in Canada, and then their timing, obviously the age of the sands that host these uranium deposits tends to be significantly younger, more Eocene kind of age. Before we get going too much with this, I just want to thank the UW School of Energy Resources and the state of Wyoming, which has been funding this research for the past couple of years. The state of Wyoming has a pretty strong vested interest in encouraging nuclear capacity building, or and which includes the exploration and potential extraction of sedimentary uranium. Then the various graduate students of mine that have been involved in this project since 2023, as well as undergrad students that have helped me collect a lot of the field work. So what we're going to go through this morning, just motivation and goals. That's just to give you some background, and then really dive into sort of the introduction and background of the location, the site area, current prospects, a little of those things. Hopefully you all are sort of familiar with the anatomy of a sedimentary uranium roll front, but we'll do a quick introduction of that. And then we'll just dive into the data. Now, for those of you that were at Image last August, you'll have seen part of this. And I've tried to add a little bit more to show you that, this is continuing research essentially. So all of the methods listed in that geophysical data, hopefully we'll get a little bit of a chance to look at. So borehole logging, which is very traditional for uranium deposits. We'll also look at some gravity, some TEM, some controlled source magnetotellurics, DC, RES-IP, SP. We just last summer collected a number of seismic reflection lines in 2D, and we'll look at a little bit of the refraction from that. I have a student still processing those reflection lines, so we're not quite there. Hopefully next image we'll have a chance to talk about and show some of that. And then we can discuss a little bit of that ongoing research that we're still kind of working on for this project. Motivation. So basically, Wyoming in the U.S. has the largest uranium reserves, and these are primarily in sedimentary basins. So this again is a sedimentary uranium deposit. Traditional exploration relies on radiometrics, magnetics, gravity surveys. Some of those, are surface more often, they're airborne. But the post exploration characterization often just relies on drilling and includes sort of total natural gamma logging, some self potential logging, and single point resistance logging on its own. This study really focuses on integrating those geophysical methods and more geophysical methods as directly applied to the sedimentary uranium deposits, and I characterize them also as shallow and deep. Currently, in this phase one of the study, we're focused on shallow, and when I mean shallow, they're very shallow. They're basically less than 32 meters below surface, so they're relatively easy to get. Not anymore as a like an excavation, as a pit mine. Usually, this is done with a flood, a water flood, that's referred to as ISR, or in situ remediation, basically. So they're flooding the zone to mobilize the uranium and pull it out of a pumping well effectively. So all of these roll fronts, that's the term for the uranium deposition in these sedimentary deposits, are channel deposits in sandstones. So just keep that in mind geologically. For this study, we included surface and borehole methods. We don't have any airborne at this particular site. We're also looking at some airborne efforts just to try to correlate as well. But for now, we're going to be talking about sort of DC resistivity or normal resistivity logging, induced polarization or IP, self potential, electromagnetic induction, magnetotellurics, or at least controlled source audio magnetotellurics, gravity, and refraction. The seismic reflection ice that we collected is still in processing, and then all of the chemistry or the geochemistry, which includes groundwater geochemistry samples, core that we've looked at with both XRF and XRD. We'll have to also wait to talk about at Image during this next year. Hopefully, we'll get into more of that. In fact, we'll get into this summer working on those deep uranium deposits, and by deep, I tend to mean 200 to 300 meter below surface. So there are other locations, other basinal locations, both in Colorado, Utah, and as well as many in Wyoming that are targets really for that effort. So we're just going to look at the really shallow stuff, and we're throwing the kitchen sink, so to speak, at these deposits that are very shallow to see what kind of efforts, and what kind of signals we get geophysically. So on top is a picture of the basin. Not terribly exciting. These are high elevation basins. Generally, the elevation on average is around 2,100 meters. You can see off in the distance a little hazy due to fire smoke, but the Laramie Range. This is Wyoming. It's very square. We're in sort of the northwest central-ish part of the U.S. And basically, Shirley Basin is a very small, intermontane basin, basically stuck between a bunch of A-type granites in the Laramies and the Granite Mountains, all these Ferris, Seminole, and Shirley Mountains. Basically, the shedding source for the uranium, if you just think of it as granite, comes from those A-type granites that are surrounding. Other basins that I mentioned, so the Powder River, Wind River, also known as Gas Hills, and the Great Divide Basin are also very productive for uranium. The main thought tends to be that the source granites producing or providing the uranium came from the Granite Mountains. It's kind of debatable in which ways, which mountain range probably contributed. In fact, there's another complication in that the Yellowstone volcanics, when there was a lot of tuff deposition in the Eocene or kind of late Eocene, basically those are also fairly uranium rich and tend to leach deeper into sand units also. So there's a lot of debate about actual source of uranium and where it's initially being sourced from. But in the grand scheme of things, it is useful to note that, there's kind of these surrounding basins to these mountain ranges tend to be the productive ones. For our particular site in Shirley Basin, we're focused on what's known as the Wind River Formation and two of the sand units that are part of it. So basically, we'll see in a minute that, the general model of a roll front, you need to have clay stones or mudstones basically surrounding a sand. Um, these these sands, as you'll see in a minute, basically are under the water table, so there has to be a recharge element to the water system that basically propagates the natural state of the uranium, right? So you need to get mobilization of uranium from a +4 valence state to a +6 valence state. That happens regularly when you have oxygen rich waters running into that deposit. As it progresses down the groundwater flow direction, the uranium deposit itself will migrate. Okay, they tend to be really slow, obviously, with time. This is a part of the Shirley Basin that's been productive since the 1940s. These zones that are in black were the producer and how much they produced over their time and at what grade. And you'll notice it's, 0.2 is a percent is basically a very productive grade for these roll fronts. This is extremely low if you were comparing it to really some of the Proterozoics like the Athabasca Basin. That's a low number, but yet volumetrically it tends to be productive enough. And so there's the reinvigorated interest in the Shirley Basin. The deposits in this area with the hash marks basically were the ones that were previously mined, and then expanded extents of the roll front are kind of shown in black. And right now, these are the various players that own mineral rights within those zones right now. Again, if you've not familiar with sedimentary roll fronts or uranium roll fronts, the idea is really a geochemical cell idea in an oxidation reduction reaction. So you have groundwater movement that's sandwiched in a sand between two claystone mudstones or semi-impermeable layers. That water basically is being channelized. As it moves into the ore, or what I like to call the ore transition zone, it changes the valence state of the uranium, it becomes mobile, and it migrates with the groundwater flow. So again, depending on how much sort of recharge oxygen rich waters are getting into this formation somewhere else up gradient, you're going to basically have different amounts of material being deposited. Again, this is there's a very detailed, understanding of these things from just a straight, gamma log point of view. One thing to note while we're here, and if you can look at this very detailed one on top or the more simplified one on the bottom, but we're going to talk a lot about the oxidized ore transition and the reduced zones sandwiched in between these semi-impermeable clay stones. So that's the fundamental model. But the gamma logging that went on from the 40s-ish to, or more like the 50s and 60s all the way through today even, is usually total gamma logging. We might wonder why we do total natural gamma now when we have more spectral gamma tools and can get a much more accurate sort of display. We'll look in our data, and that's probably another thing that's falling out of our analysis in these sedimentary basins, is that spectral gamma is a little bit more reliable to look at because you do have potassium inputs in these sedimentary environments that are usually a little rarer in those Proterozoic deposits. And so, again, just me, I always want to recommend to people that ask that they run spectral gamma logs instead of total natural gamma logs. This is just a picture. This is an older picture, probably when part of the Shirley Basin was mined as an open pit. Actually, it was also mined as a tunnel mine at one point in some parts. But this was just an old picture. You can see the oxidized zone for the ore. This A would be the oxidized or the the point where the water has already flushed out the uranium down gradient. The unaltered sandstone sits above. This is such an old picture, it's hard to see like a color change other than the darkness of the ore zone. But just again, giving you that idea of the geometry of this, hence the roll front name. At the specific site we have, it's known as agate. This is basically the projected groundwater flow direction, the surface water direction at the site, and these colors are based on the original drilling in 2023 and 2024, and estimates of the ore grade from that gamma logging. And so you can see our hot colors here are about 0.1% uranium, or uranite really. And in the grand scheme of things, even though that's a low number, as long as you spatially have, a large enough bit of that, it does still make it economic. One of my big mistakes when I first started doing this work is I thought the roll front could be mapped on a map in a linear trend easily, but it really tends to fall out of these sort of blobs, essentially. I don't know what more technical term I could use, but it's very disseminated along a general roll front trend. In terms of the effort that we put in, the first thing we started doing was collecting sort of our various geophysical instruments along these fundamental profile lines. And at the same time we were doing that, we basically, of the 100 and so, well, almost 200 wells that they drilled in an exploratory way, we monitored and instrumented about 5 of them. So there's 2 that we didn't get to before they backfilled them, but 5 of these wells basically were cased and kept open for a year and a half. And we basically took the water samples out of there, and did more detailed logging with NMR and a lot of EM logging basically in these same monitoring wells. So kind of keep this background in mind as we start going through everything. So again, just to kind of put it in context of what we know, or what we presume we know about the uranite at the site and where it's really located, our grid really was to take advantage of the 3 geochemical cells that I mentioned. So the oxidized, the ore transition, and the reduced. And if we were looking at this map, we would make the assumption primarily that this area back here is the oxidized, so it's already had reactions taking place, and it's probably just being left with a lot of iron in the pore spaces. You get to the roll front area in various portions depending on what sort of disseminated blob you're running across. And certainly then to the southeast in this map, we're running into anything that's reduced, so unaltered at this stage. We'll start just really quickly looking at the logs, and basically we'll start just looking at the difference between uranium. There's a lot on these logs, so we're looking at the NMR data, so porosity, the water, the actual mobile water that's there, the uranium, which is the green curve, the EM conductivity, which is the red curve, and then the IP, which we'll talk more about in a second. But for the short run, if we're just looking at differentiating clays, obviously the EM is where we want to go, and we probably have to, this is not looking at that top clay. The top clay is above this level just slightly, so this view is really focusing on the sands itself. So, but even so, in the productive uranium sand, we do have these kicks every so often of clay that starts to, you can see it both in sort of the EM curve, obviously, and if you're looking at the porosity curve, you're usually looking at a low point in the NMR data for that. So, but that being said, we basically have this well here, which is in the reduced case. We don't really see any uranium. That green is pretty much flatline. There's a couple small bumps that are organics, but you know, nothing that significant. As we move into various parts of the roll front or the transition zone, we have 3 wells actually that go through those bits. You can see reactivity in that green line, which is the uranium, getting pretty significant. In fact, these two wells actually sample that upper and that middle uranium sand that I mentioned in the geology initially. And then the last well really hits that oxidized where we're not in any uranium. So again, our uranium curve is basically almost, sub 100, counts essentially, or ppm. These are spectral gamma curves again, so that's why I can basically talk about uranium in terms of its ppm value as opposed to just a total API count rate. Again, so we're keeping track of, in that uranium sand interval in all of these wells, we're basically keeping track of the clays that show up and the amount of uranium that we see. So those are primarily the things that the production companies actually care about. But if in this work and in work I presented an image, we were looking at an IP response. The reason I even started this effort was I'd been very familiar with a lot of NAPL, DNAPL, and LNAPL degradation, which also is another form of an oxidation reduction reaction series, and it providing IP responses in the time domain. And so it seemed very likely that it was possible we would get that. And so there's a lot of IP, not just uranium-based IP signatures in the sand, which are the yellow arrows, but we also have a membrane, sort of a sand polarization that happens in a few places, and even a slight clay. I mean, believe it or not, the clay IP response is much more muted generally, but it's still there. So we'll get to those when we look at some of the surface profiles a little bit more, and you'll hopefully agree with me that there's a lot more work that we need to do to understand the IP response, but fundamentally it's there. So that's a good thing to at least start. So again, I'm going to give you guys takeaways as we go, because otherwise if we waited to the end with a bunch of conclusions, it would probably be overwhelming and feel like we're drinking from a fire hose. So basically our spectral gamma responses, which I also imply are more useful than total gamma by themselves, basically show that we're less than 100 ppm in the reduced zone. We're generally fairly high, 1,000 to 1,500 in primary parts, or very high level parts, or high ore zone deposit areas, I guess. But in the transition zone, so in that area where we're kind of getting those parts of that arcuate curve that are disseminating towards the reduced, we still get 250 ppm. Oxidized responses are again even smaller than either the reduced or the ore, and they're less than 50 ppm generally. EM logging is very useful for highlighting the clay zones. I think a little bit more useful than traditional normal resistivity curves. I haven't had a chance to compare with like a lateral log, but nonetheless, traditionally out here, at least, they're relying on SPR and SP logs, which have a little bit of problem because the zone above the ore zone is dry, right? So to get these electric logs, they have to flood the well, and therefore they're altering the SP response. So I feel like it's a little silly to do the SP, and SPR is fine, but in some ways EM logging kind of gets around the whole problem. We are very interested in what total porosities are, let alone how much water is being mobilized in those zones. That's where NMR logging comes in very handy to give us estimates of total porosity. We see that there really isn't a whole lot of change, which we wouldn't expect it either. But if we look at the ore transition zone, it is slightly less porous than the reduced and oxidized zones. I mean, you're going to have fill in the pore space. It's probably different fill between those two fundamental bits of the geochemical cells. So there's just very likely to be things going on in the ore transition zone, filling up pores, and different things, different chemicals, different mineralogies filling up pore space in the reduced and the oxidized zones. IP logs give us an understanding that there is an IP response at these things, so it's actually sort of useful. It's assumed at this point that the 40 to 60 millisecond chargeability is electrochemical. when you've got the uranium nearby in that zone of the ore transition, and generally around the same levels for the non-uranium sands. And for the few clays that actually kind of show up, they tend to be a little bit higher, but there's just less of them. So we still have to work on how we differentiate those things. And we'll talk about that more a little bit later. Now, just to throw other methods at the problem, especially because this is relatively shallow, let's talk really quickly about gravity or relative gravity, transienium, and controlled source magnetotellurics. Idea here is to get ideas about density and resistivity in those three, geochemical cells or redox zones. So basically, we don't have time to step through everything, but we'll go. Here's the basic Bouguer gravity map that we produced from last summer. Basically, it's not terribly exciting. There isn't a huge transition across the entire site. I think we're getting a strong advantage from the fact that these things are relatively close to the surface, but we have to continue modeling. And I've got a student kind of working on that right now to basically understand how deep, how big, can we actually see. So there's the ore grade map is kind of below here. This is just the Bouguer contoured map. But what was more useful, obviously, at this site was looking at the first horizontal derivative of that map. Along sort of a 45-degree axis. If we're calculating to calculate the derivatives, the reason of picking 45 is trying to be along what we presume the groundwater flow direction is. We know the groundwater flow is driving a lot of this. So we want to basically see, and when we when we do that, if we put our wells here that we were looking at earlier, we were assuming everything out here was reduced. Here's our roll front. We're at the nice edge of that, first derivative anomaly, and then behind it, basically we're in the negative zone in our oxidized holes. So again, there is some use here. The scale of how this could get used generally, we're still working on, but it was very encouraging, to see that, yes, it's possible at this particular site to look at, the first derivative map and get something useful. Now, the reason there's two, you see this trend here and you see a couple trends here. Don't forget, as I mentioned earlier, these deposits are generally thought to live in channel sands, so braided channels within the deposition of that Wind River Formation sand. So it's not terribly surprising that you see a roll front here and then another isolated roll front here. This one up here has yet to be drilled, so there's still the jury is still out, so to speak, on how productive this one really could be. But we know, and we already have sort of characterization of ore grade potential along this one. So we'll see. They're supposed to start drilling that part next year. So we'll find out if that gravity gives us any clue about what's going on. But let's switch now to go to transient electromagnetics. It's really tempting to want to run these on these sites because we already suspect a large resistivity difference between those zones. This is a summary map of 102 soundings across that site, where we have 42 in the reduced, 31 in our projected ore zone, and 29 in the oxidized. This was collected with a walk temp 2 with a 40 meter TX and two RXs of 10 and 1.5 meter, right? The interesting thing is, we're kind of showing in the zone of the ore sand, which is kind of highlighted by this circle, the resistivity in the ore zone is lowest of the three redox zonations, right? And then our reduced actually is next, which was a little bit of a surprise. I thought the reduced area would probably be the more resistive, but it turns out the oxidized is, and we're still trying to formulate that because there's always been this sort of understanding that in the oxidized zone, it's going to potentially contain a lot more ferrous iron. And so why wouldn't it be a little more conductive? I'm not sure. It's certainly a reflection probably of the pore space fill. Um, we've we've learned one thing, and I'll mention it kind of in the get to the takeaways here, though, that when we are in these sedimentary basins that have high claystone, mudstone contents, TEM tends to attenuate fairly quickly. And so it works really well in this site because those deposits are really shallow. But as soon as we try to apply it in deeper basins where we're looking at that 200-meter zone, we just don't even get to any signal from the target interval just because we're basically attenuating too much. We're not going to show, I'm not going to show too many examples of that, or I'm not going to show any examples, excuse me, I should be clear. But when we come out after this summer's effort, when we're really focused on those 200 to 300-meter targets, they'll, I'll probably pull in a slide at that point showing how the attenuation just gets too much. If we switch then to controlled source audio magnetotellurics, right, it's a very relatively deeper sort of EM method generally, but we can still get away with testing it here on these shallow deposits, and in the hope that if we see anything here in these shallow deposits, this may give us a little bit better resolution on those deeper targets this summer. And we'll be studying that. But at this point, we did 78 locations. This was all last summer, 32 reduced, 17 ore zone, 29 oxidized. This was all collected with a Stratagem 5 with an external CSAMT transmitter about 500 meters away generally. The interesting thing of note here is that our ore zone is still a lower resistivity. No surprise, that's good. That's what we would have expected already. But in this case, the ore and the oxidized and the reduced zones tend to overlap each other, at least at this place. And so, we can't necessarily discriminate them. They're a lot high. They are higher though in a resistivity sense than the ore zone. So it's conformational. Hopefully this summer when we apply MT or shallow MT or CSAMT to those 200 and 300 meter deposits, we'll get some interesting results. But at this point, it's good to understand what we're looking at. So again, takeaways. First, horizontal derivative gravity map highlights the roll front that we know about. It is shallow and laterally variable, but it is, remember, low uranite, 0.1. So we are ongoing with gravity modeling, determine scales, depths, and volumes that influence this response. So I can't really tell you at this point if I feel, it'll work for those deeper scales. We'd like to get more of a understanding of, fundamentally what could go on before we make that attempt. But surface TEM, when it's averaged and combined and looked at in sort of the understanding of what the redox state are, we can see that low resistivity in the ore transition zone. This is not new. We would have expected this. This was talked about and discussed 20 years ago. But the reality is we can quantify this. So at least at this site, we can understand it a little better. It does sort of bode well theoretically that the electric methods, either resistivity or IP, should also highlight some changes across that zone. And we'll talk about those in a minute. Yeah, and then I mentioned, it's TEM's great for these deposits at this particular site, but when we go deeper, it's kind of failed a little bit. So bear that in mind, depending on the depth of the target you're interested in. The AMT does better, giving information from deeper zones, and we still see that ore zone resistivity lowering, which is useful. Now let's kind of go back and we'll look at just a few of the surface data sets. I mean, we could spend hours looking at all we've collected these last couple of years, but we're going to just pick a few. So this line 5 first, we'll look at the refraction data first. This is the refraction data determined, or the refraction model determined for refraction statics for the reflection data set. So we're still working on getting the reflection data set done, but we've got the refraction statics part of that already done, and we can actually do a tomography of that. So here is our area. This is the sort of the reduced area out in front of the ore zone, which is in this well in 16. The interesting thing is that we've got at the top of the sands velocities basically lower in what we assume are these channel structures. But the interesting thing along line 5 here is that we see an increase in velocity at the ore zone well versus the reduced well. So it looks, or if, at least indications are at this point, that we increase the velocity due to an increase in bulk density. Now we have to confirm that, but it doesn't seem like it's too big of a stretch. On top of that, I'm showing the SP curve. So you can see that the SP activity really starts in earnest right where we know the roll front to be. So again, sort of confirmation that there's something going on and changing in the subsurface. If we look at the resistivity, this is surface resistivity done with a low power instrument. So we can see again differentiation between any of the top clay-ish. You can see it's variable, so we don't have a whole lot of top clay when we're down in this low part of the valley, but as we go up this ridge that's to our north, we basically increase. And the sands tend to be resistive but variable. So how reliable is that change in resistivity across there? Can we say anything about the roll front itself? I think it's difficult, right? I mean, it's interesting. We see what we expect lithologically, right? We have low resistivity clays, we have higher resistivity sands that vary, and then we have the bottom clays, which are extremely low again. But in terms of resistivity on its own, I wouldn't necessarily say this is the only thing you have to do to help delineate. But when we get into IP, that's where things start to shake out a little better. So this is that same line. So we're in the reduced area out here. We have no real IP response, a little bit at depth. But as we enter the zone where IP is already, expected to be from that drilling result, we start running into anomalies at the depth we would expect within the sand. So this hashed square is essentially the sand layer depths that we care about. Now, this also shows us the complication I mentioned earlier in the borehole data, that in our IP data, we're basically seeing clay dominant IP in the time domain. So we got to be careful. We can't just say every IP thing represents uranium here. As we thicken in the clay, we get more of a clay response, right? I said there was very little clay over here. We see very little IP above the actual area of the target sand. But as we go into the thickening of the clay, we start to get that. And whether that actually, it probably is masking out anything that might be below it if it's there. So we have to, we're working on some more full decay modeling of the IP data and acquisition of the full decay series this coming summer. So hopefully we can make some more, kind of interesting arguments about time domain response and reality on these deposits. But it'll have to wait a little bit. But it's encouraging to see that the geochemical oxidation reduction reaction is something that can be noticed here in the IP data. All right, I'm gonna go a little fast through line 6 and the next one we do, which is one of the cross lines, line 15, just because, again, we're kind of getting shorter on time and we're seeing the basic same thing. So again, this is another north-south cross sect. We see the same sort of, there is no refraction data that I can show you at this time. That's still being worked on. So again, we see the same response, but here we go from an ore zone area here to an oxidized area over here. And again, we got to be careful about some of these resistors that expand to depth. There is a possibility that there's some structural things going on here that we're not quite seeing yet. We're waiting for the refraction or reflection data on that. But again, on our IP response, let's focus on that for I6. We know at well 90, we have a really high lower sand or middle sand kind of IP response in the borehole data and stuff like that. And we basically see it on the surface too. So in fact, and then we get out into this oxidized area. So this area is spent and we really have no significant IP response. So that's encouraging. Now we'll look at this cross line and we call this this is line 15. Again, we have refraction model for the refraction statics at this point. And we can basically look between this well here, which is an ore zone well, and this well out here, which we weren't, this was a well that got filled in before I could turn it into a monitoring well, but before that we got all the logs out of it. So we're basically looking at a reduced well out here, and we see a much larger sort of dipping or lowering of velocity going a little deeper. So we might actually be traveling within more of this channel structure. Hopefully, again, we'll see more of that pop out as our reflection data comes in. You can see again with the SP data that this area here is pretty active, especially in this area around the known. So that's also encouraging. The res results, basically it's the same conclusions here. At line 15, we have variable amounts of the clay above the sands, but our sands are still sort of variable. Some of these lows could represent parts of the roll front, but then again, it's not very unique. It's a little harder to discriminate, really. If you didn't have the borehole information, it would be really difficult to know, that what may or may not be sort of an ore zone roll front relevant kind of resistivity response. But when we go back to the IP along this line, this is got basically two zones, this one further to the west, and then this one that we cross that basically give us IP responses. And again, we're in a zone where the top clay is not very thick, and so it's not generating a time domain response. And so anyway, and then as we get out into the reduced area again here, we don't see much. There is a clay IP in the borehole. That's this yellow right here, but we don't really see it at depth and the known sand interval. So that's encouraging. This is just a schematic I showed at image where we're looking at line 5 again. So we've got the geochemical cells on top, so the reduced, the ore transition, and the oxidized sort of listed, and kind of picking out that clay response near the surface. So again, we have to work on this sort of filtering of the IP data a little bit to figure out how we can not get kind of taken aback by these lower time domain responses that are fairly significant, and focus on the ones that we really want to target, which are in these guys right here. So again, refraction data is giving us indications of channel structures and velocity increases that might, or at least now, seem to correspond to these ore transition zones. We're hoping an ongoing reflection work will look deeper into that sort of interpretation. Self-potential anomalies are also turning out to be pretty useful to highlight the electrochemical potential produced by the redox reactions. We know that they're not electrokinetic, so they're not really flowing water SP anomalies, because we have monitored the water levels for over a year at this site, and basically our flow rates are ridiculously slow. So we're not looking at a high normal flow rate, so there isn't really fast movement to this roll front if you want to think about it that way. But typically we're looking at about obviously less than a millivolt, so but they're still distinguishable from background because there shouldn't be any electrochemical SP if we don't have some kind of chemistry happening. DC resistivity distinguishes the bulk changes, but the resistivity anomalies with depth are difficult to distinguish, really. So on its own, it's not quite good enough to distinguish fundamental redox zones. But at least at this site, we have yet to find one that it sort of does that. Even though we saw in the TEM data and the CSAMT data that ore transition resistivities are lower, there tends to be enough of them that it's really hard to distinguish when you get on site. So in the general, right now, time domain IP tracks the roll front, right, versus that electrochemical polarization going on at the ore transition zone. So, but that being said, we're not seeing that exclusively. We're getting membrane polarization in some of the sand and clay layers, as pore space gets filled. So we see that, and we have to be aware of that. And we're working on trying to understand if there's ways in the time domain, at least, that we could potentially separate those two a little better. And then there's a thought maybe in future to look at sort of spectral IP and if those same sorts of zones and anomalies could distinguish that way too. So that's definitely ongoing work that we're transitioning into this coming summer, in addition to that targeting of the deeper, quote unquote, uranium. So again, this is, I don't really need to go over this again. Effectively, I've mentioned it. So we're looking at full decay sampling this summer. Also with low power systems and high power systems. So we have a high power 10 kilowatt capable system. So we can, use that for those deeper 300-meter targets to get both resistivity and IP. Our reflection profiling is ongoing. We collected 6 lines last year, 3 vertical only and 3 component. And again, we're focused primarily on structures, paleo channels. There is a hope that an amplitude phase anomalies might exist at the ore zone. So, we'll look into that as this year continues. And generally, the thing that also is really missing from all that I've showed you today is really the supporting geochemical and water level information. So we've got water levels in the 5 monitoring wells across a single recharge season. We've done 4 samplings across those 5 monitoring wells, 3 which are in the ore transition zone, 1 in reduced, 1 in the oxidized area. And then we've done XRD and XRF on cores that were taken from those sands in 4 of those monitoring wells. So we've got a lot of geochemistry to then start to apply to why we're seeing what we see in the geophysics. So hopefully, again, another potential talk at Image this year will be not only the reflection work we've done, but that integration of understanding the geochemistry in the water and the rock, and basically attributing those conditions to the geophysics data that we see. And with that, I'll let you go and take any questions. Remember, just go ahead. I don't know if Lori, if anybody can actually talk, or if this is all Q&A from the chat box, but please go ahead. Thank you for your time.
Yep, I think it's just the Q&A box at this time.
Okay.
So if you have a question, please put it in the Q&A box. It's found on the right-hand side of your screen. And yeah, we'll get to them. There was a question. The individual wasn't sure or clear on why you didn't use the normal gamma ray and the RT to define the clays, and then look at the SP.
Yeah, that's a great question. So we basically have those data. So the original sort of understanding from the sort of our corporate partners exploration is to just do that natural gamma, and that's fine. We looked at that, and when you compare, and I don't have a slide for it here, unfortunately, but if you look at sort of the spectral gamma uranium response, you can basically track that to a certain extent within the natural gamma response. But like I said in my discussion, I'm a little more keen on using spectral gamma versus total, because these sedimentary basins actually have a little more significant potassium response that also adds in, and you can start to use that almost as a discriminator, in addition to the SPR and the SP. And again, I'm a little not happy about how when we do the SP logs in the borehole, we're basically having to flood that thing. So in the agate site, you've got basically a DTW, or a water table, that's at about 22 meter depth. And then our ore zone basically is right there. So at 26 to 28 typically. And so to get useful information out of a well that's not drilled very deep, because they really avoid drilling through that bottom clay. They don't want to do that. They don't want to provide, water pathways out of the formation. So they only drill into the sand, and as soon as they get to that bottom clay, they stop. And so that isn't very good for, the length of most normal resistivity tools. And therefore it's a little tricky. And so they get around that problem by flooding it. So as soon as they flood it, though, they're generating electrokinetic responses in the SP. So that becomes a little bit tricky. So that's why I started to rely only on the EM log, which was a normal EM, not a lateral log, but still they would be similar. So effectively, if you could do those to get at your clay response, that's a little bit more reliable when you have to backflood. Now on deeper ones that are well below the water table, it should be better. You should be able to use your SP curve like you would normally.
Okay, thank you. We have lots of questions coming in.
Okay.
The first one, what is your gravity station spacing?
Okay, nominally it was 50-meter across that site. There was a few areas that we were kind of got tacked on and asked to look at the end, and so a few of them are 100-meter, but nominally it was 50-meter spacing. And then our gravity base was basically on a part of the site that was in the reduced area, so theoretically to the southeast in front of the roll front, which should have a minimal gravity signature.
Thank you. The next question is how does 3D reflection seismic data using nodes can help? Could you explain about the parameters that you use for this survey?
So for this survey, yes, we had GTI nodes. And so they were spaced every 2 meters. So it's not exactly, I mean, if we were looking at a true sort of near surface reflection survey, I probably would have been biasing a little bit more towards a meter for our station spacing. But at this point, we were just exploratory, it being a little bit exploratory. For all the lines, we basically had a 2 meter station spacing and shot spacing. Now, in terms of the shot itself, because these were pretty shallow and we wanted high frequency, we did some supporting modeling with the velocity profile that we estimated here from previous refraction data to basically, we wanted to be around 400 hertz nominally for our reflection signals. And so we ended up using a sledgehammer, honestly, which is not going to be useful for this summer, in fact, but when we're going deeper. But for this particular site, we could kind of afford an impact source, and we would just basically hit every other. So it would be a 4 meter kind of station spacing.
Thank you. Is this site under active pumping and production? And would that affect your monitoring wells?
Of course. The simple answer is no. This is not a produced site yet. And so we don't have any active pumping going on. They've just done the basic, kind of exploratory drilling at this stage. Now, I'm not the best one to ask if they plan to. I'm always a little humored by these companies because a lot of the times they get involved in these projects, but not really to produce, but to sell. So essentially, we were given access to their particular site. All the information we've got is interesting. If they use it to start producing, that would be great in a lot of ways. But I totally am on board with you. And actually, my original proposal included the idea that if we were at an active site with pumping going on, we could also study those effects. And could something like IP be more used as a monitoring tool to watch what happens with the well field essentially when they start production? But that being said, that was a great idea that has yet to come to fruition since nobody has actually taken these sites to production. So I wish I could answer that, but I can't, not yet. But it's a great question.
All right, thank you. We have our next question says, thank you so much for this great talk. Is it true to say that the valence should be from +4 to +6 in order for the uranium to be either extractable or of economic importance?
Correct. Yeah, I can simply answer that. Yes. Basically, you need to change that valence by the flood of the ISR, right? So that it basically becomes mobile with whatever the oxygen rich waters are that you're pumping in there. Most of the time, they're surface waters, theoretically. But, in the natural state, like we were looking at here, you're assuming that up gradient, there's some kind of, in our case, probably snow recharge, that's basically getting into the formation and causing that reaction to be mobilized.
Nice, thank you. Well, our next question. I hopped on at slide 15, but did you grab stationary spectral gamma at zones of interest? Are there peaks that correspond to gamma emitting isotopes?
Yes, let's bounce back there for a second. So, um, it's tricky, right? So we have peaks that are flanking larger IP peaks in the wells that matter, right? So basically, here we're still in the sand, but our uranium peak is slightly shallower. Same kind of, well, actually, this flanking well and well 20, the peak and the uranium peak sort of correspond, but it's also slightly siltier. So yeah, it's a little trickier, and probably we should go back. And there are quite a few logs. In fact, right now I'm just showing the 64-inch IP with a 500 millisecond injection window. So we actually did 100 and 250 also. So we could look at a much more broad spectrum of IP response. So there is some peaks, and one could maybe argue that they're close, but if they directly overlie is a little bit tricky. I'll be honest with you. That's a great question, though.
All right, thank you. Our next question is there any distinguishing magnetic response expected to distinguish between the reduced ore and oxidized zones?
Simple answer is I wish. I didn't show you, we do have magnetic susceptibility logging from each of these 5 wells also. You'll see that it's pretty much in that extremely low, almost negligible magnetic susceptibility range. Generally in these sedimentary basins and associated with Shirley and a few of the other basins, I've not seen magnetics that's correlatable with the uranium roll front as much as basement, basement rock types and rock changes. So right now, I would say magnetics is not as helpful so far. I've yet to see those responses be useful enough for us to warrant, flying a mag survey with a drone or even walking survey just to see if we get more responses. But from the borehole mag susceptibility, it was extremely low and basically negligible. So we've kind of walked away from magnetic looking, and so far in these basins.
All right, thank you so much. Any additional questions for our presenter? All right, I don't see any new questions coming in, and we are actually right on time.
Well, great. Thanks. If you have any other questions, please feel free to email me directly. Hopefully my email's scattered around some of these things. But yeah, as I said, hopefully this is ongoing work. So hopefully at Image we'll have a couple more presentations on the various aspects that we're continuing to work on, as well as those looking into sort of the deeper uranium deposits. And so hopefully we'll have a lot more sort of exciting stuff coming out in the next year or so.
All right. Last chance for questions. All right. There's a question about the recording of this webinar. We are recording, so I imagine that everyone who is registered will have access to it, either on the SCG On Demand page or the SCG YouTube channel. And it will be under the, oh, look at that. If you want to look for future webinars on a variety of topics, keep your eye on the SEG events webpage, and also follow SEG events on LinkedIn. That's where we post for all of our webinars. All of my webinars are free, so tell your friends. Anyone can join and participate and maybe learn something or two. So yes, so I will put the webinar in the SEG On Demand or on our SEG YouTube channel. So that's it. And look forward to our future webinars on both the Europe Regional Advisory Committee, the Near Surface Hydrogeophysics Subcommittee, and also the Global and Student Subcommittees. So that's all I have to say. Thank you very much, Brad. Excellent presentation, enjoyable questions and answers. So, yep, thank you. And thanks everyone for attending. Have a great day.